Section: Introduction. In this section, we aim to understand the training of neural networks, which is a key focus in deep learning. This understanding is crucial for improving training methods and addressing AI safety concerns. However, the complexity of the optimization process, characterized by high dimensions, non-convexity, and randomness, makes it challenging to analyze thoroughly. We recognize that the learning rate, LR, is a critical hyperparameter in gradient descent optimization. It determines the size of the steps we take during optimization. Due to the complex nature of the loss function in neural networks, the LR significantly influences the solutions we achieve after training. Starting with large LRs, especially at the beginning, has become a common strategy. This approach helps us avoid poor local minima, and the solutions we find often exhibit good generalization and a flatter loss landscape. Previous research has explored the advantages of high learning rates from various angles, focusing on optimization, model sparsity, and pattern learning. However, we still have important questions. How large should the LRs be, and what are the characteristics of models trained with different LRs? For the first question, a general guideline suggests starting with an LR that is too high for convergence but too low for divergence, though specific benchmarks are lacking. Regarding the second question, despite extensive literature on LRs, we still do not have a clear understanding of how models trained with small versus large LRs differ. To address these issues, we conduct a detailed empirical analysis in a controlled setting that allows us to manage the LR precisely. We categorize different LR values into three training regimes. Small LRs lead to convergence, medium LRs create chaotic equilibrium, and large LRs result in divergence. We first examine the generalization of final solutions obtained by fine-tuning with small LRs or through weight averaging after training in various regimes. Our findings indicate that starting training in the second regime, with moderately high LRs, yields the best results. Specifically, a narrow range we define as subregime 2A consistently provides optimal outcomes. We further investigate the effectiveness of these learning rates by analyzing the loss landscape and feature learning. We discover that training in subregime 2A leads to a basin in the loss landscape with well-generalizing minima that are linearly connected. In contrast, using too small LRs can create instability when fine-tuning with larger LRs, while excessively large LRs may overlook good solution basins. To explore feature learning, we introduce a synthetic example with interpretable features. We find that as the LR increases up to subregime 2A, models become more specialized, relying on fewer features. However, beyond this point, the ability to extract useful features diminishes. We also demonstrate that our findings apply to practical image classification tasks through frequency analysis of input images. In summary, our contributions include comparing the generalization of minima reached with different initial LRs, confirming that starting with LRs above the convergence threshold is beneficial. We identify that subregime 2A consistently leads to optimal results, locating a convex basin with good solutions. We also reveal that NNs learn a sparser set of relevant features as the initial LR increases, but this ability declines after subregime 2A. Our conclusions hold true for conventional neural network training as well, and we have made our code available for further exploration. In the related work, we note that much research has focused on the training dynamics of neural networks, particularly the role of the LR hyperparameter. Many studies highlight the positive effects of large LRs, attributing these to the noise in stochastic gradient descent, SGD, which helps avoid suboptimal local minima. While these studies suggest mechanisms for the benefits of large LRs, they often lack a clear characterization of the resulting solutions. We also explore the relationship between training with different initial LRs and input space feature sparsity. Contrary to previous findings that indicated a consistent increase in sparsity with larger LRs, we observe a non-monotonic behavior, with the most significant sparsity effects occurring at LR values that also yield the best generalization results. Additionally, we examine how different learning rates affect pattern learning, noting that smaller LRs tend to capture more complex patterns. We build on the idea of opposing signals in data, showing that training with large LRs can help filter out unreliable features. Our work provides further insights into the features captured by models trained with varying initial LRs. Section Summary. In this section, we explore the impact of learning rate, LR, on neural network training, emphasizing that starting with moderately high LRs, specifically in the subregime 2A range, leads to optimal generalization and stability in the loss landscape. We also find that while higher LRs initially promote feature sparsity, excessively large LRs can hinder the model's ability to learn useful features. Section: Methodology. In this section, we explore the methodology we use to study the effect of the initial learning rate, LR, on the final outcomes of our models. To do this rigorously, we fixed the LR at the start of training. However, since most modern architectures incorporate some form of normalization, truly fixing an LR is challenging. Normalization leads to two main issues. First, the weights become scale invariant and are essentially defined on a sphere. Second, the effective learning rate, ELR, changes even when the LR is fixed, due to variations in the parameter's norm. To address this, we trained our models while keeping the parameter's norm constant in a scale invariant way. This approach allowed us to ensure that fixing the LR also fixed the ELR. We made all our models fully scale invariant by fixing the last layer and removing trainable parameters from the normalization layers, training them using projected stochastic gradient descent, SGD, on a sphere of fixed radius. We found that training scale invariant models typically falls into one of three regimes based on the LR value: convergence, where parameters steadily approach a minimum; chaotic equilibrium, where the loss stabilizes with noise; and divergence, where the model performs randomly. We adopted this three-regime framework for our analysis. In our results, we illustrated the test accuracy after training with various fixed LRs, clearly showing the three regimes. While we primarily focused on training with fixed LRs, we noted that starting in the chaotic equilibrium regime and then reducing the LR often leads to better outcomes than maintaining a constant LR. Other studies support this, suggesting that beginning in the chaotic equilibrium phase benefits from the noise-driven stabilization process. To further investigate, we divided our training into two stages. First, we conducted pre-training with different fixed LRs, which we termed PLRs, for enough epochs to stabilize the training dynamics. After pre-training, we either adjusted the learning rate for fine-tuning with a smaller LR or continued with the same LR and averaged the weights from subsequent checkpoints, similar to stochastic weight averaging, SWA. For fine-tuning, we only used first-regime LRs, referred to as FLRs, to ensure convergence. We provide more details about our experimental setup in the appendix. Our main results, obtained using a scale-invariant RESNET18 on the CIFAR10 dataset, are presented in the following sections. We also considered other architectures and datasets, which are detailed in the appendix. For clarity, we divided all plots into three sections corresponding to the pre-training regimes. We start by comparing the generalization of the fine-tuned SWA solutions from different pre-training LRs. Next, we analyze their local geometry to understand their differences better. We then examine feature learning in models trained with various initial LRs and propose a synthetic example with adjustable features. Finally, we confirm that our findings apply to conventionally trained networks as well and draw our conclusions. To assess the generalization benefits of the pre-training stage, we evaluated the test accuracy of the fine-tuned SWA models. We analyzed pre-training in each regime, highlighting the range of initial LRs that yield the best final results. In the first regime, we observed a clear relationship between the PLR value and the test accuracy of the pre-trained model. Both SWA and fine-tuning with FLRs less than or equal to the PLR did not significantly alter the pre-trained accuracy. However, fine-tuning with FLRs greater than the PLR could notably enhance test accuracy, though it still did not outperform training from scratch with the same FLR. Thus, the optimal strategy in the first regime is to use the highest constant LR without any adjustments. Section Summary. In this section, we investigate the effects of fixing the learning rate, LR, during training, addressing challenges posed by normalization in modern architectures. We establish a methodology that includes pre-training models with fixed LRs across 3 distinct training regimes, followed by fine-tuning or weight averaging, to optimize generalization and test accuracy. Section Regime 2. In this section, we explore Regime 2, which is the most effective for pre-training, as most practical learning rate, LR, schedules begin here. We observe that the results are highly influenced by the pre-training learning rate, PLR, value. The general guideline of using a large LR for better solutions holds true, but not for all PLRs in this regime. We can further divide Regime 2 into 2 subregimes, 2A and 2B. In subregime 2A, where we use lower PLRs, we find that pre-training leads to significantly better fine-tuning and stochastic weight averaging, SWA, results compared to Regime 1. However, in subregime 2B, with higher PLRs, we lose this advantage. Although pre-training with lower PLRs does not achieve the lowest loss values, it helps us find optimal areas for fine-tuning or weight averaging. Notably, fine-tuning a network from this range with any fine-tuning learning rate, FLR, yields similar quality minima. This approach allows us to fine-tune even with small FLRs, avoiding poor generalization that often results from training from scratch with these FLRs. Moreover, the fine-tuned models are of higher quality than those from Regime 1, indicating that the best minima may be unreachable with small LRs from a standard initialization within a reasonable training time. In subregime 2B, increasing the PLR diminishes the benefits we gained in subregime 2A. Both SWA and fine-tuning quality decline, and the solutions from different FLRs start to diverge in test accuracy. Thus, pre-training can be counterproductive if we switch to a lower LR from this regime. We previously noted that high LRs in the second regime can harm final model performance for single-step LR schedules. However, we find that gradually decreasing the LR through subregime 2A can alleviate this issue. Overall, achieving high-quality results in this subregime with SWA or fine-tuning using a constant FLR is not feasible and requires a more complex LR schedule. Moving to Regime 3, we see that pre-training here resembles random walking in the parameter space, making it impractical for weight averaging. Nonetheless, it can still be useful for fine-tuning with small FLRs. We believe this is because pre-training in this regime creates an uneven distribution of norms among parameter groups, leading to higher effective learning rates for some groups. This unevenness promotes better convergence during fine-tuning. While pre-training with large PLRs from the first regime finds points with decent test accuracy, these points cannot be improved through fine-tuning or weight averaging, making the first regime less ideal for starting training. Pre-training with lower PLRs from the second regime, just above the boundary with Regime 1, effectively enhances quality beyond what a constant LR can achieve. However, using higher PLRs negates this advantage and worsens performance. Although pre-training in Regime 3 does not seem to extract useful information, it may still provide better initialization for subsequent fine-tuning. From a loss landscape perspective, we have identified the range of initial LRs that yield the best model quality. Now, we aim to clarify the characteristics that set these LRs apart. We analyze the local geometry of minima obtained after initial training in different regimes by measuring linear connectivity and angular distance between them. The angular distance between two networks with weights is calculated using the cosine of the angle formed by their weight vectors. We use this as a natural metric in the weight space. Linear connectivity is assessed by calculating the highest difference in error along a linear path between two networks. The barrier value indicates whether solutions from the same pre-trained point remain in a low error region or diverge to different optima. We present angular distances and linear connectivity for 3 solutions for each PLR, SWA of 5 networks and points obtained after fine-tuning with the lowest and highest FLRs. As previously shown, small initial LRs from regime 1 do not improve the pre-trained model through SWA or fine-tuning with smaller FLRs, as they remain in the same minimum. Conversely, using a much larger FLR can lead to a significant improvement in test accuracy, indicating a shift to a better minimum. In summary, pre-training with small LRs can lead to unstable minima, while using initial LRs from the optimal range in subregime 2A allows us to find a basin of high-quality solutions that are easily reachable through fine-tuning or SWA. Larger PLRs fail to locate low-error basins and instead explore vast areas of the loss landscape with diverse, non-linearly connected minima. Section Summary. In this section, we analyze the effectiveness of different learning rate (LR) regimes for pre-training, highlighting that pre-training in subregime 2A with lower second regime PLRs leads to better fine-tuning outcomes, while higher PLRs in subregime 2B degrade performance. We also find that pre-training in the third regime, although less effective, can still provide beneficial initialization for fine-tuning with small FLRs, while emphasizing the importance of using optimal initial LRs to locate high-quality solution basins in the loss landscape. Section: Feature Learning Perspective. In this section, we explore how different learning rates, LRs, affect feature learning in our models. To do this, we create a synthetic example that allows us to control how various features influence the target variable. We set up a binary classification scenario with 3 key aspects. We observe all 3 training regimes. Changing the initial LR leads to different generalization outcomes, and each data point has multiple features that can independently classify the data correctly. We work with data vectors that have 32 dimensions, where each pair of coordinates represents a 2D feature, and all 16 features come from the same distribution. We utilize a 3-layer multi-layer perceptron, MLP, with ReLU activation and layer normalization, ensuring it is scale invariant like our main setup. More details can be found in the appendix. The generalization and geometry properties in this setup align with what we previously described. To assess how features are learned with different LRs, we create 16 single-feature test samples, each containing only one of the 16 features. The other features are distributed along the decision boundary to simulate missing features. We evaluate the accuracy of our trained models on these single-feature samples, linking the accuracy to the importance of each feature. Higher accuracy indicates greater importance. We analyze these values in sorted order for each learning rate since models may prioritize different features due to random initialization. Our findings show that with small learning rates, there is no effective feature selection, leading to similar accuracy across different features and poor overall generalization. As we approach the boundary between the first and second regimes, we notice a specialization in the model. The accuracy for a single feature becomes significantly higher than for others. This feature sparsity continues even after fine-tuning, indicating a shift in feature learning behavior compared to the first regime. Even when features are equally useful, the model tends to focus on a subset rather than trying to learn all features simultaneously. The peak in feature sparsity in the second subregime coincides with the highest fine-tuning test accuracy, suggesting that a sparser set of learned features enhances model generalization. When we increase the learning rate to the second subregime, the model's ability to extract useful patterns diminishes, resulting in lower accuracy on both regular and single-feature test samples. We also observe a similar feature selection effect in a scale-invariant RESNET18 model trained on the CIFAR10 dataset. Since defining features in real-world image data is challenging, we use frequency bands from the 2D discrete Fourier transform, DFT, as a proxy for features. We divide the full 2D spectrum of an image into 4 components: constant background color, low frequencies, mid-frequencies, and high frequencies. For each component, we zero out the rest of the spectrum and apply the inverse DFT to create images that preserve only one frequency component. We repeat this process for each test image and measure accuracy on the resulting 4 new test sets. Our results show that with small learning rates, the model treats all features similarly, slightly favoring background color and low-frequency features. As we increase the learning rate, we see feature sparsity emerge, with mid-frequency features becoming significantly more important. The peak accuracy for mid-frequency features occurs in the second subregime, surpassing the accuracy of the other components. After fine-tuning, mid-frequency accuracy improves further, demonstrating a similar bias towards a subset of features as seen in the synthetic example. However, increasing the learning rate to the second subregime reduces feature sparsity and the importance of mid-frequencies. Since mid-frequencies are crucial for model generalization and robustness in image classification, their prominence in the second subregime indicates that feature selection is not random but favors the most useful features for the task. Interestingly, while previous research suggested that training with large learning rates prioritizes easy-to-fit but hard-to-generalize features, our results indicate that the model may actually prefer more complex features if they are more beneficial for predicting the target. Using initial learning rates from the second subregime leads to sparse feature learning, allowing the model to concentrate on the most relevant features for the task, resulting in improved generalization. In contrast, pre-training with other initial learning rate values does not exhibit this model specialization. Section Summary. In this section, we investigate how different learning rates, LRs, affect feature learning in models, using both synthetic examples and real-world image data. Our findings reveal that lower LRs lead to poor feature selection and generalization, while optimal LRs promote specialization towards the most relevant features, enhancing model performance and generalization. Section: Practical Setting. In this section, we demonstrate that our main findings can be applied to a more traditional training environment with some differences. We train a standard RESNET18 model without the sphere constraint, using stochastic gradient descent with momentum, weight decay, and data augmentation. The only difference from the usual setup is a modified learning rate schedule. Due to the unstable behavior of weights that are not scale invariant with large learning rates, we can only observe two regimes. The boundary between these regimes is less distinct, mainly because the data augmentations make learning more challenging. As a result, the model does not fully converge with small learning rates, so we estimate the boundary based on the learning rate that yields the best quality at the pre-trained point. Our first claim, that the highest quality is achieved when learning rates drop at the start of the second regime, is confirmed. We also find that fine-tuning in this subregime leads to similar optimal results, regardless of the initial learning rate, while larger learning rates result in varied outcomes. In the first regime, the behavior is quite different due to convergence issues. Even small learning rates can still enhance quality. Notably, in the best points of the second subregime, fine-tuning achieves a test accuracy of around 95%, comparable to a standard learning rate schedule. We observe that linear connectivity is maintained in both the first regime and the second subregime, but is lost in the second subregime B. The small training error barriers at the start of the first regime arise from the large learning rates. Additionally, the accuracy of frequency bands shows a similar trend. In the second subregime, the network captures significantly more mid-frequency information from the inputs compared to other ranges. In the appendix, we provide further practical results, including analyses of stochastic weight averaging, angular distances, and test error barriers, as well as experiments on CIFAR100 and Tiny ImageNet. We also illustrate how our findings apply to vision transformers in the appendix. In summary, our main claims hold true in practical settings, and most results from controlled environments are relevant to real-world applications. Regarding the convergence threshold, we assert that the best initial learning rates are just above this threshold. The convergence threshold separates the two regimes, meaning that training with a constant learning rate below this threshold leads to convergence, while a higher rate prevents it. Convergence is defined as the training loss approaching its global minimum by the end of training. In simpler setups without advanced data augmentations, we can track this by the model's ability to fit the training data. However, we note that the convergence threshold is better viewed as a small range within the overall learning rate spectrum, as it may shift slightly based on factors like the number of training epochs. We can efficiently find this threshold using methods like binary search on learning rates. In practice, precisely identifying the convergence threshold isn't essential. While optimal initial learning rates for fine-tuning are just above this threshold, larger learning rates can still yield similar final quality if a more sophisticated learning rate schedule is employed. Most practical schedules start with a high learning rate and gradually decrease it, so we recommend beginning training with a reasonably high learning rate from the second regime to achieve a good final outcome. We have shown that the best learning rates for pre-training help identify a region in the loss landscape with good solutions and also focus on the most useful features. An interesting question arises about how these observations are connected. Based on our results in the second sub-regime, we suggest that learning a subset of features corresponds to locating a specific area in the loss landscape, where solutions depend more on these features. The features learned during pre-training can influence the quality of the solutions found in this region. This leads to intriguing questions, such as whether we can link the properties of learned features to characteristics of the solution basin, like sharpness. Solutions obtained with higher learning rates in the first regime tend to generalize better and have lower sharpness, although this relationship is more complex for fine-tuned solutions in the second regime. We also wonder how feature sparsity impacts the properties of the solution basin. Does it define a specific set of shared features, or can it act as a regularizer, leading to simpler models that can be represented by smaller networks? Exploring these issues is crucial for future research in neural network training, as it may connect the optimization process with the final properties of the model. Section Summary. In this section, we demonstrate that our findings can be applied to a conventional training setup using ARESNET18 model, revealing that the best learning rates, LRs, lie just above a convergence threshold, which separates different training regimes. We also explore how the choice of LRs influences feature learning in the loss landscape, suggesting that optimal LRs not only identify beneficial solution basins but also promote feature sparsity, which could impact model performance and generalization. Section: Practical Implications. In this section, we highlight several important practical implications from our experiments, even though they were on a smaller scale. First, we confirm that using higher learning rates, LRs, not only accelerates training but also helps the neural network discover solutions that lower LRs cannot reach, which was previously noted only in specific cases. Next, we emphasize the importance of selecting both an initial LR and a comprehensive LR schedule. A well-chosen initial LR helps us find the best solution region, as very low LRs often lead to suboptimal solutions with poor generalization. Additionally, if we start training with a high LR, we need to carefully manage its decrease, ensuring we gradually explore optimal values to locate a good solution basin before convergence. We also observe that the initial LR choice can influence how features are learned. In our experiments, we found that sparse features and mid-frequency bias were linked to better generalization. However, this may not always hold true in practice. For instance, some features that help classify training data might not be useful for test data. Moreover, while training with high LRs reduces the likelihood of memorizing a small data subset, some studies suggest that memorization can be beneficial in neural networks. Thus, the effects of different LRs in more complex scenarios, especially with misleading features or benign memorization, could create intricate relationships between LRs and generalization. We believe exploring this area is crucial for future research to better understand how learning rates impact trained models.